Hello, everyone. Good morning, good evening, good afternoon, wherever you are. Welcome to another one of the great storage debates where we take a look at some of the big questions of storage and ask the storage questions that are on everyone's mind. Here we go beyond the naming of the parts and dig a little deeper into some of the hows, the whys, and the things you need to know about different ways of solving storage problems. Today's presentation is going to be on centralized and distributed storage, which are the foundations for practically all modern storage architectures. And today we're lucky to have huge names in the storage industry, and then there's me. My name is Jay Metz, and I'm going to be your intrepid host and moderator for today's engagement. And presenting the case for centralized storage, we have John Kim, who happens to be the SNIA Ethernet Storage Forum Chair and comes to us from Mellanox. Hello, John.
Hello, Jay. Great to be here.
Great. Mute buttons are all found. That's excellent. And presenting the case for distributed storage is SNIA's Ethernet Storage Forum Vice Chair, Alex McDonald, who hails from NetApp. Hi, Alex.
Hi there, Jay. I'm John. Good speaking to you.
Excellent. So our sponsor for today's presentation is sponsored by the Storage Networking Industry Association, who has the support and participation of thousands of industry professionals just like you. From standards to education, from testing to compliance, SNIA is the go-to organization for all things storage. Now, one quick detour into administrivia, if you bear with me for a second. We'd like to point out that while the material contained in this webinar is copyright by SNIA, any member organization or individual members may use the material as long as the slides are reproduced in their entirety without modification, and SNIA is acknowledged as the source. To that end, let me address one of the questions that always comes up. As usual, these slides will be made available after the webinar is over at a link that we're going to provide at the end of the presentation. Now, speaking of questions, we want to keep this presentation to under an hour, and we have a lot of material to cover. So we want you to ask questions, but if we don't get to your question live on the webinar, we will answer it in the blog afterwards. I also want to make note of two very important buttons in your browser window. The first is the question button. This is an interactive session, and we really want your questions. And I'll do my best to make sure that they get inserted into the appropriate time and as time allows. The second, and this is critical for us on the webinar, is the feedback and ratings button. Please don't forget to leave a rating, and if you're feeling particularly moved, leave some feedback. A lot of work goes into these presentations, and your feedback is extremely important to us so that we can know if we're on the right track. One last bit of advice. Sometimes we get comments that the audio may be hard to hear. If you're listening through your web browser and have lots of tabs open, we found that clearing your cache can sometimes have the desired effect of improving the audio quality. However, there's nothing we can do about getting my voice as good as John's or as interesting as Alex's. So, before we get started, it's important to know how we're going to approach this. In any debate, you need to know what the rules are. Obviously, that's what we're doing now. We're laying down the rules, not just for the participants, but also for you, the audience. Yep, that's right. You're as much a part of this as the speakers are. We're going to be breaking down the presentation into two rough parts. In the first part, we're going to be discussing what is centralized storage and what is distributed storage, and talk a bit about how they work. The second part, that's the part that you likely came to see, is where we start looking at the trade-offs, understanding some of the things you need to know about each of the technologies in a comparison and contrast kind of way. Now, at the risk of stealing everyone's thunder, I want to point out, despite the title, that this is not about choosing a winner or a loser. Those of you who have already seen some of the great storage debates already know that we're really looking to talk about the sweet spots of the technology, rather than declaring victory of one over the other. If you're one of those people who are looking to find out which approach is better for you, then our job is to give you the information you need in order to make an informed decision. For that reason, John and Alex are here to help define the technologies, explain how they work, and discuss the trade-offs that occur when using them. Now, to that end, it's up to me to do a little bit of level setting first. Storage has one job, and it's very, very important that it does that one job correctly. And that job is to give me back the correct bit I asked you to hold on to for me. Now, truthfully, many people that the key phrase in that sentence is hold on to for me. In reality, the key phrase is give me back the correct bit. Everything we do in storage, which includes networking as well as architectures and topologies, is based around completing that job safely, securely, reliably, and without error. And therein lies the rub, without error. Now, think about it for a second. Without error. What do you need to do in order to make that happen without error? What does it mean to have a storage system that can do this without error? Well, no matter what system you choose, that means you have to need to protect the data and keep it secure. And often that can mean that you have oversight by some form of government regulation, and that means you have to have systems in place that form compliance. What's more, not only do you have to be able to do this without error, but you have to know that you're doing it correctly, which means that you have to be able to manage that storage. Of course, if you're going to do it without error, you can't simply hope that your data is going to be there all the time. Hope is not a strategy. Bad things happen all the time, which means that if you're going to reduce the risk of error, you have to back it up. Now, all of these things are needs. That is, the requirements. Non-negotiable. Nuh-uh. Gotta have them. But there are also a few nice-to-haves, too. You may need, for example, to grow over time. That means that the system should have some mechanism for scaling, whether that's in terms of capacity or in terms of access or in terms of performance. Sometimes you need to share that data, not just in terms of users, but also in terms of applications. Sometimes different types of data is time sensitive. Sure, you may be willing to wait just a little bit longer for your friend's Instagram photos, but other types of data, like financial data, for instance, needs to be very, very fast. All of these needs place pressure on the overall system. So what is your job then? It's important to keep in mind that not only your criteria for success is important, but also your criteria for failure. When we go through the remainder of the debate, and I'm almost done here, I promise, you need to know how to evaluate these different solutions. It's useful to keep in mind that storage isn't just data at the end of the wire. It's an end-to-end situation that can get pretty complex. You need to understand how you access that storage, which in turn can lead to impacts on performance. You need to understand whether or not the kind of data can tolerate being unavailable, which is not the same as data loss, by the way. It just means a measure of how much time it takes to get to it. On top of how much storage capacity you need, you also have to weigh in the data protection side as well, not to mention how much the system is going to cost. How much is your data worth? And that's why, as we finally get to the topic at hand, you should keep these in the back of your mind as the criteria for choosing one method versus the other. And with that, finally, I hand the controls over to John, who is going to take us down the path of centralized storage. John?
Jay, thank you very much. Let's talk about centralized storage, but first, as we go into it, let me give a few quick definitions. So first, direct attached storage is storage that's directly attached to one server. I'll illustrate that in a few slides. A storage area network is centralized storage that's usually one array shared by multiple servers connected by some sort of storage network using block storage like Fiber Channel or iSCSI or NVMe over Fabrics. Network attached storage is also centralized shared storage supporting multiple servers but connected with a file protocol. And then hyperconverged infrastructure is where you have a set of servers that are sharing compute and storage resources, and it's usually distributed, but not always. So, but typically you have a bunch of servers that have local storage, but somehow share it with each other as well as sharing their compute power. So, having given those definitions, what we usually see in the evolution of storage is most companies or IT data centers or IT departments long ago, it started with local storage, and many people still do for small projects or getting started because local storage is very easy. You put storage in each server. It's often easy to buy. You can order the storage when you order the servers. It's installed by your system integrator or your server vendor. It's very easy to set up. All the operating systems, all the applications, all the hypervisors understand local storage and can typically just use it without any special drivers. But as Jay said, storage not only needs to return the data you put in there, but you need to be able to back it up. You need to be able to make sure it's secure. You need to be able to possibly replicate it. You may want to make it efficient with some sort of data reduction techniques. And you need to worry about how much storage you have. And local storage sometimes suffers from issues of utilization or backup. It can be kind of hard to secure it and back it up and make sure that you have the right amount in each server. It's very common with local storage that some servers have too much and some servers don't have enough. So there was been a move to centralized storage, especially as IT departments or projects get bigger. They tend to consolidate the storage into a centralized system where one storage array supports multiple servers and you connect. There are many ways to connect, including PCIe and SAS, but once you centralize storage, the most common ways are SAN, NAS, or with an object protocol. Using connections like fiber channel or Ethernet usually are the most common. It's also easier to share and protect the data in this case, and again, Jay mentioned the importance of that. So when all your data, your databases, your files are centralized in one place, it's usually a lot easier to make a snapshot or a copy or a clone or back it up to tape or back it up to disk or make a replica in another location. You also have an easier time with utilization and efficiency because you can buy a bunch of storage and assign the right amount to each server, and each server gets just how much it needs, and you can give more or less storage to each server in the future. So that's an advantage of centralized storage. And just showing a diagram, here we illustrate some of the concepts we talked about in the definitions and the previous two slides. So we have internal storage. I have a server. I have internal drives that are connected either to a SAS or SATA adapter or to the PCIe bus if it's NVMe SSDs. Or in the middle example, we have direct attached storage. We have a server with some kind of a host bus adapter or other adapter that connects to usually a fairly simple, just a bunch of disks, JBOD, or just a bunch of flash, JBOF. And on the right, we show centralized network storage. This could be SAN or NAS. We have multiple servers connected, usually through a switch, to a centralized storage array. And this storage array usually has some kind of sophisticated software and some intelligence or smarts that allows it to do things like provisioning, maybe compression, deduplication, instant backups, to do replication, all from that centralized location. So in that case, I could make one backup or do one replication, set up one replication, and the data for all those servers can be backed up or replicated at one time. And a chart comparing some of the different types of storage, how they connect. So I won't go through every line, but we can see as we look at internal storage, direct attach, SAN, NAS, object, and hyperconverged, that we can see where the storage usually is, how it's connected, how it's shared, and whether or not it's distributed. And focusing on the last two columns, we can see that with internal storage and direct attach, you really don't share anything. Every server has its own. With SAN and NAS, you can share the storage. You do share the storage, and you might be able to share the files. With object storage, you share at the object level, and sharing is always possible. It's not always done, but it's always possible. And then in terms of distributed, we see that, again, internal and DAS are never distributed. SAN can be, but it's not very common. NAS could be if you have scale-out NAS, and Alex can talk a little bit more about that. Object is usually distributed the way it's designed, object storage. And hyperconverged might or might not be distributed depending how it's set up. Some hyperconverged systems actually can still use centralized storage. So having done that, I think that's a good overview of centralized storage, some of the benefits, and then I would like to hand it back over to Alex to talk about distributed storage.
Thank you, John. I hope you can hear me because I gave a presentation a couple of weeks ago where nobody heard me at all, which was not very satisfying for everybody involved, that included me. I spoke to myself for an hour, but hopefully you're getting my dulcet tones this time. So, now without further ado,
I can hear you, man. I can hear you.
Thank you, Jerry. So in terms of distributed storage, defining distributed storage for me is particularly devilishly difficult because it in effect is the hole in the donut. If the donut is centralized storage, then the hole is where the distributed storage is. Everything that centralized storage is not. And I'm going to take a fairly loosey-goosey approach to defining it and even including cloud-type implementations. But so it's difficult to precisely define, but let me try. So the data is generally stored on many systems which look like a single entity. So all we're building things in parts and then pulling them together and making them look like a single entity from the end point of the application or the user, from their perspective. It might be geographically, very often it's geographically or regionally dispersed rather than local to a data center. So it actually lives across geographies. It can be accessed over a LAN or normally, more typically rather, a WAN, and it's commonly Ethernet based. So these things tend to live in disparate places, brought together, and look cloudy-ish. They're often implemented on shared resources. So the more cloudy your storage looks, probably the more decentralized it is. It's certainly not centralized storage, that's for sure. And I'm kind of going to give up at this point because I'm just going to simply say it's not centralized. And it's not necessarily hyperconverged, or hyperconverged can live in the cloud. So these definitions are to be taken with what can only be described as a bucket of salt. You know, the partitioning is very much a case of this dark grey over here and this light grey over there. The other important thing, though, in terms of distributed storage, it scales out rather than up. In other words, when we build more of it, we do it horizontally. We get more of the same kinds of pieces and build out horizontally and bring them together rather than up vertically. In other words, we don't make the individual pieces bigger. We don't add more big disks to make up our distributed storage. We tend to add more disks and distribute our data out. So in terms of, let's talk a little about the access and performance of distributed storage and how it compares and contrasts. And the first thing is to look at, there's a little diagram on the right-hand side. It's a little bit faded in color. I do apologize for that. There's an attempt to demonstrate the difference between two key aspects in terms of the performance and the way that we connect to our data, and that is bandwidth and latency. Latency is the length of time it takes to get down the wire, and the bandwidth is how much we can put down the wire. And if you think of that in terms of, for instance, a water flow, I always think of it in terms of the bigger the pipe, the more water you can carry, and the latency is it's pretty difficult to make water move faster than a given speed. You know, speed of sound, for example, is pretty limiting when it comes to moving air around. So there's a limit, and the latency you can't do very much about. There's a great quote I always have, a quote here: bandwidth problems can be cured with money, latency problems are harder because the speed of light is fixed. You can't bribe God. So classically, bandwidth issues are engineering problems, and latency are just physics, can't get around them. But that gives us an immense problem because in terms of geography, if we're doing distributed systems, then we have these latencies between two sites, and there are a variety of ways of getting around this, but I'll talk a little about them in a minute. The compute location is important here because low bandwidth and poor latency can be tolerable if the compute is next to the data. And that's key, again, in the distributed environment. It's moving the compute out to where the data is. And then we only need to send and receive small amounts of data. But I'll, again, cover that when we talk about some of the topics further in. The protocols tend to be application-driven, obviously, but the protocols tend to be in the distributed storage, object-type storage through things like S3, CDMI, Swift, or LAN or WAN protocols like SMB and NFS. They're commonly used on distributed storage. And block, occasionally, you sometimes see block storage being used, particularly iSCSI, in distributed storage environments. So it's not beyond the wit of people to develop your block systems and build file systems or directly attach database applications to block storage. But as a rule of thumb here, I'm going to do a real quick one. The less cloudy or WANy the access, then the less likely the application will tolerate high latency and or low bandwidth. Applications generally like low latency and high bandwidth. They like being next to the source of the data. And that's an important key when it comes to building distributed storage systems. We need a different way of thinking about our applications as well. So I'll talk about data security and privacy, which is always a big issue when we're out there distributing things, and also because we're beginning to share resources more and more. Security is about making only sure the right people and systems have access to the data, and privacy ensures that the data isn't misused. We're not going to talk about privacy today. That's explored. There's actually a link there that talks about the GDPR and privacy issues with the data and how to make sure your data remains private. But the security measures that you can employ are things like identification and authentication systems. Identification is who you claim to be, and authentication is making sure that you are who you claim to be. And there are systems out there like Kerberos and LDAP that allow you to build secure identification authentication systems over the top of your storage. You need to be thinking about end-to-end encryption. That includes the devices at the back end. Encrypted storage is going to be incredibly important in terms of securing your data, particularly if you've got sensitive data. And storing the data in the right place and knowing how the data is managed is important as well. Nothing worse than actually filing your storage, your application data out to some storage that's distributed to find that the backups are being taken from, for instance, Germany to France, and perhaps you're breaking.
Uh-oh. Did we lose you, Alex? I heard a bump.
Oh, I'm sorry. I'm back. Gosh, technology. Is that me back?
Yeah, I got you back now. I got you back,
sorry.
man. I got you back.
So just to reiterate, about the right place for data, knowing where your data is secured and stored, and that includes things like replicas and backups, is absolutely essential in terms of building security in a distributed storage environment. I do beg your pardon about the loss of sound there. The other thing about distributed is scaling out rather than up. The capacity can be can be seen as infinite. You can scale these things out quite readily to very large sizes and think that it's just a matter of cost. But as soon as you do that, more capacity tends to exacerbate some issues you need to think about. First one, you've got more cold data. Anytime you start putting data out in large volumes, you're going to find that the quantity of cold data you're storing increases as well. You need higher bandwidth. The fact is that there's a statistic I saw recently that we in fact have doubled the capacity, but the bandwidth has only increased by about 1.5 times. So there's a bandwidth crisis coming as well. You've got a higher bandwidth requirement the more storage you have out there. It's harder to avoid putting compute with data. You've got to think about where is it you put the compute. You can't move around terabytes of data readily to process it quickly. And more distributed storage is appearing at the edge of our known manageable environment. And we really need to start thinking about processing it there, things like the Internet of Things, but I'll cover that in a second. And I'll also cover in a second data amnesia, which is forgetting what data you put where, and that's becoming increasingly so difficult. And also we'll talk about later about some of the system management problems that comes with scale, in particular in scaling out. So what about protection and durability? How do we protect this stuff? Well, distributed storage can use a variety of technologies, like standard RAID, that's used in centralized storage systems like SANs and NAS boxes. Or we begin to see things like mirroring and replication being really common too, perhaps even 3 copies of the same data being stored in different locations. Erasure coding, another technique that's used to ensure that the data is protected. And there's actually another webcast we've got, Storage Basics Q&A, and No One's Pride and Shirt. This is all about protecting data and the durability of data. The other thing we can do is think about our data a different way, and there's something called the CAP theorem. I'm not going to go into great detail here, and the diagram on the right gives you an example of that. Some applications use different or require different types of ways of thinking about our storage. And the CAP theorem is about, is the data consistent? In other words, if I write a transaction, does every location see the same transaction or the effect of that transaction? Is it available? In other words, can I see my data at all times? And is it partitioned? Are there pieces of my data available in one place that might be available also in another place should the network fail? So the CAP theorem allows us to pick 2 of these 3 attributes in terms of distributed storage. And applications as a consequence, and some of them are shown there, it's pretty small. You can actually explode this out if you wish to show that bigger diagram. Show, for instance, some database technologies that use different approaches to consistency, availability, and partitioning. So what is the future of distributed storage? I think it's really fascinating. This is why I think where all the growth is. Well, I know where all the growth is. It's got new and interesting solutions that are new database technologies, some of which are in that diagram, like NoSQL, like key value, like tabular databases. There's on-disk compute, where we can do compute on the disk. So I'll give you an example. You can do processing on the drive, data classification. And instead of the traditional database technique of getting back millions of records to find out which ones are for products that are less than $2, what we can do is actually go out and ask the drive, how many records do you store for products that are less than $2, and just get back the answer, 247 of them. And instead of actually having to transfer all the data, the drive is helping us with the smarts, and we're pushing that compute, or at least partial compute, out towards the edge and out to where the place where the data is born, and we're actually dealing with the data at the place where we're generating it. The Internet of Things also is generating huge amounts of data that we need to cope with at the edge. And this is the new future of distributed storage. How do we build systems that allow us to manage big data right at the edge of our known, if you like, known application universe? And these are really interesting questions that distributed storage is beginning to answer for us. So, Jay, over to you.
Excellent. We've got the general gist of the what's in the hows of the centralized and distributed. So let's take a quick look at where we are. Centralized storage, then, and if I'm wrong about this, I know we have it on the screen, but John, you can correct me, and Alex, when I get to yours, you can correct me as well. But centralized storage then capitalizes on the ability to be more efficient about storage utilization. It helps consolidate some of the management functionality that's required to let storage do its one job. In other words, when we look at our criteria for success, we can see that we've centralized that responsibility. And conversely, a distributed storage system is designed to scale out, not up. Because scale is the biggest concern, we're willing to trade off some of the performance and management focus in the attempt to gain scale. So is that a fair description?
Jay, I would say that's absolutely fair. I would just comment that on the centralized storage, it always makes the management of the data easier, and it makes the management of some storage tasks easier. But centralized storage can also make some storage task management a little more complicated, and I'll talk about that later.
Okay. I know I've got distracted when Alex started talking about donuts. I have a donut desire now. Anyway, so I blame Alex for that. So here's where we get to the nitties and the gritties, folks. Let's bring it on. What are the trade-offs here? The question now turns then to the issue of how each of these different approaches handles the needs that we talked about earlier. And before we do, though, I want to say that if you have any questions for either John or Alex, this is a great time to get them in the mix. Feel free to ask your questions using the appropriate button in the browser, and I'll do my best to insert them into the conversation at the appropriate time. And we did get a question that came in about the slides. Yes, the slides are going to be available, and I will be handing out the link at the end of the presentation. Okay, so for now, let's see. What are the trade-offs? And the first topic up for grabs is data locality. Let's start off with the most obvious, to me at least. If you have centralized storage, it implies a greater degree of focus on where that data is located. So just how important is data locality? And John, we're going to give you a crack at this first.
Yeah, Jay, with centralized storage, data locality is very important. You almost always need the servers and the storage to be in the same data center so they can have a fast, low latency connection of whatever network type you're using between those two. It is rare that you're able to have the centralized storage in, say, one location and the servers in a different location across a WAN link. Usually that's just too much latency and it hurts the performance too much. Occasionally with object storage it's allowed, but generally not with block or file centralized storage. So what you find you have to do is if you have remote offices or branch offices which have servers and users in there that need storage, is you have to install some smaller centralized array in those remote locations so that the servers out there have have locality with their storage. As I mentioned, object and file can support remote access if the performance isn't critical, but that's usually for applications or users who can tolerate a fair amount of high latency. So for a regular file share, maybe a user in a branch office could be accessing a file share in a central data center, but then they have to learn to just wait that extra couple of seconds when they want to access a file. Or they could set it up as distributed storage, but I'll let Alex cover that part.
Well, to that point, Alex, why don't you cover that part?
Actually, really interestingly, a question has come in that kind of summarizes this. Well, I'll answer the question first of all. Data locality, is it really important? Well, with distributed storage at scale, data locality is really quite hard to achieve. There are types of distributed systems you can build in a single location, but in general, distributed storage is all about distributing the storage, and we're trying to generate data at the edge. We're trying to store it, manage it at the edge, more than we're trying to move it to the center. Centralization of data is quite hard because data's got mass and inertia. It's difficult stuff to push around, and it's actually easiest to process it where it's born and to centralize the summaries, for example, and do partial compute, the thing I talked about earlier, at the edge. Also, then there are new technologies that prevent this extreme form of centralization that we've come from. So, for instance, blockchain and distributed ledgers, those are done in a very distributed fashion. And in fact, the entire distributed ledger is held multiple times over in multiple nodes in multiple different places. And that's actually a key function, the distributed nature of it. It's not just an add-on at the end. It's the distributed nature that makes it what it is. So the question was, computation faces an analogous debate between distributed compute versus centralized compute. What is the balance between centralized, distributed, et cetera, And it very much depends on the application. You can have distributed compute and centralized storage. Don't know quite how that would work. However, having distributed compute and distributed storage works really well. And I think we're going to see an awful lot more of that kind of compute at the edge along with data at the edge, and a completely different scale of management when it comes to distributed systems. Quite different. My other example was about video and image as well. So imagine you're collecting video and image, and this is a simple example, and we know that, for instance, Google can categorize photographs. There's an image search technology that they have for one, and they have a variety of other technologies that do this as well. But if you're collecting data at the edge in terms of photographs on my iPhone, for instance, which is going to some part of the cloud, then processing it locally makes a lot of sense. I can categorize it about where the photograph was taken. My iPhone knows that. And then I could perhaps categorize when it's stored by looking at the face and facial recognition on it. So the various parts of compute can be done at various levels within my distributed storage environment. I can't do that in a centralized fashion. It's just too difficult. That's a long answer to a short question.
But sometimes the easiest questions have the most complicated answers. I think that one of the things that we're getting to in this entire debate is that the trade-offs is that yes, you do have the advantages of a lot of the scalability and being able to distribute not only the compute as well as the storage, but you're also adding in additional layers of abstraction in order to manage this at the upper level, right? So the trade-off here is that you're adding in additional software to basically get that bit back, and there are also trade-offs when that happens. So to that end, when we get to that scale, what are the consequences and what are the impacts that we're looking at? And I think that, John, you can probably run away with this at this point.
Sure. So when you have centralized storage, it's usually what we call scale-up storage, which means that when you reach the limits of the array, then you have to get another array because you can't keep expanding it. And when I talk about the limits, what will happen is you set up centralized storage. Each array will have some kind of limit, usually a performance limit and a capacity limit. And you buy the array, and then you can keep adding more capacity to it until you reach the capacity limit, or until you hit that performance limit, and then you have to add another array. The other issue is the network may have some kind of limit. So the connections from the server to the switch, or in the switch, or the connections from the switch to the storage, the network can have some kind of limit, typically a bandwidth limit, or there may be a budget limit where you can't afford to expand the network more, to keep expanding the performance of the network. And there's also the issue, as we mentioned, that you may require locality. So we have in the illustration here, I have the server on the other side of a WAN link, and that WAN link, whether it's to another branch office or to a server in the cloud, or a local server to storage in the cloud, adds latency. And it also probably has a bandwidth restriction. So when you go across the WAN, you may have the latency too high, or the bandwidth may be too low. So the other thing is that your staff has to develop some expertise. So while centralized storage simplifies management because, in one location, or if it's a very big installation, several locations rather than dozens of servers, I can back up the data or protect it with RAID or snapshots and replication. I do have to train people or hire people who know how to manage the software on that storage and know how to manage the network. I may have to build a separate network, separate from my regular network, to handle that. And so that can require additional expertise and work in order to gain the advantages of centralized storage. So you have advantages in managing the data, but there's some additional work in managing the storage. New knowledge is required to manage the storage and the storage network.
Yeah, and the question just came in that actually touches on this, but I'm going to let Alex go first and answer that question, answer the distribution of scale, for distributed scale. And then we're going to get to the question that just came in, because I think that's actually belongs here. So, Alex, why don't you go ahead and make your case first?
So, the easy answer and the simple answer, and the one that is very attractive in how to scale distributed storage, is simply to just add more. But that's not really an answer that I think most people would accept as being a real answer. There are lots of issues in scaling distributed. Although it technically scales quite easily, there are limits. The ones I put here, there are four of them really. Economics, you've got cost. Scaling can be a really expensive proposition, especially where geography is involved, and you have to pay for your bandwidth, and you have to pay for low latency, as far as you can physically get low latency, that is. You've got legal issues, you maybe have data placement issues. Quite a lot of data that we collect nowadays has actually got some legal requirements as to data placement, and there are two pieces of legislation that make a big difference here. One is GDPR, the General Data Protection Regulations in Europe, and then there's a thing called Safe Harbor, which applies to US-based companies, and various other jurisdictions have laws of their own. China, for instance, the stuff stays inside China. You just don't get the opportunity to move it anywhere else. And then you've got technical issues in terms of bandwidth and latency. I've already touched on slightly on those. They're related to cost. Latency you can't fix, though. And then the fourth one is the application. Not all distributed systems can actually scale out to infinity. There are some limitations, and if you look at the CAP theorem, this thing about consistent, available, and partitioned, then you will start to see some of the issues that applications face. And the one I use here as an example is an airline booking system, whereby booking seats on planes is something where you think you're actually getting a seat. When you click on the seat number and you press OK, if you've ever clicked on a busy plane and booked a seat, you've sometimes been rejected for that seat, gone back to find that it's been filled. Reason? Somebody else got there before you. Or maybe not. Perhaps your transaction just didn't make it to where it was supposed to be going. And there are limitations in this in terms of scaling out to infinity. Can you imagine literally tens of thousands of people trying to book airline seats on the same plane? Now that kind of thing, although it's not imagined in terms of an airline booking system, you can think of other systems that have these issues of scale. So yeah, there are issues. In the main, just add more, but be aware of those four major limitations.
And I think that segues into the question that came in about the latency issues, and particularly the part of the cap limitations. The question is, for the record, is there a document that has cataloged the impact of latency on the many data types? And the point being that it would be very useful to have a single source of truth about what latency budgets different protocols and different storage types have for designing storage environments. I have my own thoughts on it, but John, you want to try to answer that question first, and then we can go to Alex.
Sure. I don't think I can give a complete answer to it, but I can certainly start. So there isn't a single document that documents all this, but people who work with applications and network storage, or storage in general, generally develop an idea. So, for example, databases usually are less tolerant of latency and like lower latency connections. Applications that use block storage, running virtual machines and hypervisors, they usually want storage with a low latency connection if you're going to use network storage for that. Applications that can handle higher latency often include file shares for when users are just storing their home directories on like NAS. Usually the users may not admit it, but they can usually handle much higher latency in terms of typical storage. You could have many milliseconds or even a couple of seconds, and they're probably still going to be productive. Web pages might be able to handle a little more latency in databases, but not as much latency as say a home directory or a regular file share. But that doesn't mean all file applications handle high latency. There are many scientific or technical or oil and gas or video processing applications that use file storage, but they also want very, very low latency in order to get good performance, because they're doing a lot of transactions. Every transaction has a latency overhead, so the latency stacks up and really hurts your performance or makes the processing take much, much longer in the end, even if it's just a few extra milliseconds of latency multiplied by thousands of transactions every minute. Object storage often tolerates higher latency, partly because the applications that are designed to use object storage sort of are built with the expectation that it's going to have higher latency. So they're sort of designed both from a software and a user expectation standpoint to handle that higher latency. So I'm going to end it there. I'm not sure. I don't think I've completely answered the question, but let me turn it back to you, Jay and Alex, if you want to expand on that answer.
Well, just really
I think
quickly.
That's a good answer.
Yeah, just really quickly, I don't think there's a document, but there's an awful lot of talent and experienced people inside storage vendors that can help you answer some of these questions. The one application that I would suggest requires the lowest latency of the lot, right at the top of the list, is a restore. So anytime you're thinking of data recovery, if data recovery is important to you, then low latency on restores is essential. You know, what do people want when things fail? They want to restore immediately. And single latency in that respect, I mean, that's a different way of looking at it. But no documents, plenty of experience though.
Yeah, and that tribal knowledge can both be, very helpful if you happen to know the tribe, and very frustrating if you don't. There are some protocol head-to-heads that have been done by various analytical firms. But you also have to keep in mind that a lot of these things are based upon the lowest common denominator. And generally speaking, different types of storage environments are better suited for different types of networking environments. And so when we start to basically talk about the different data types, we have to make certain assumptions, and usually those assumptions are not grounded in reality. You have to, like, for example, we assume that the network is reliable. We assume that the network is homogeneous. We assume that topology doesn't change. And I'm just reading off the list from, Tannenbaum's book of distributed systems, which somebody tweeted out earlier this morning. It just happened to fit perfectly into the question. I mean, generally speaking, the reality is that no matter what document you have, you're still going to have to rely on what the vendor recommended versions are, and what the application recommended versions are, or recommended budgets are. And that's going to be important to note that there really is no shortcut to this one. You're going to have to do your homework, unfortunately. Now, having said that, and looking at the time, I think we should probably move a little bit forward and start talking about the idea of sharing resources. And so, John, tell me a little bit about how you'd characterize sharing resources from a centralized perspective.
Absolutely. So when you share the resources, typically you manage each array separately. So I probably didn't write this that well, but when I say the arrays are not shared, what I really meant to say is that you manage each array as an independent unit. Now, you may be able to have one admin or one network for the arrays, and you may be able to use one set of management tools. So if all the arrays are from one vendor or a similar model, or if you have a management tool that's flexible enough to support different brands of centralized storage, you might be able to use one console or management tool that looks at them. But even in that case, you have to sort of look at the capacity and performance of each array separately. Now, whether it could be good or bad, but you may very well have different types of centralized storage arrays for different workloads. So different storage arrays are often better at different kinds of storage. One might be really good at block, another might be better at file, another type of centralized array might only do object. You may have one array that's all NVMe over Fabric or NVMe flash for the lowest latency but at a higher cost, and another array that's full of big hard drives that gives you really a really great price per terabyte, but is slower and it's lower bandwidth and higher latency. So the good news is you can have different kinds of arrays that specialize in different workloads or different types of storage media. And the bad news is you're managing different arrays separately, and the wider the variety or the more differences between the arrays, then the more work it is to manage all of them and to take care of it and to keep track of making sure that all the right things are happening on all the different arrays.
Cool. And obviously shared resources from a distributed perspective, really is where it shines. So Alex, why don't you go ahead and take off from there?
Well, shared resources are what distributed systems are really all about. Even GCHQ or the US equivalent, the NSA, share resources and like to secure it and make sure that people don't leak it. And Edward Snowden being an example in point. The data location is a movable feast. So there are some issues with sharing. Data location, you've got to think about where the backups end up, where the mirroring is done. If you're sharding. There are a variety of technologies that allow you to lose control of data location, and these are just a few of them. Recovery scenarios can be really complex on a distributed and shared resource environment. In fact, there used to be the old joke that the only person a restore really made happy was the person who'd actually screwed up in the first place, because everyone else that had their files restored around about them were really quite desperately unhappy. So there's this issue about recovery scenarios being really quite complex, and who and what is impacted by failure and what restore criteria you have. Do you take application level restores rather than data store level backups? You need to understand the security and privacy, obviously, and the impacts on performance that are to do with noisy neighbors, as an example. If you've got somebody who's consuming 9/10 of your bandwidth, and are moving massive files around your distributed storage system, then that could be an issue if you're actually trying to get access to your data in a shared environment. That's shared everything, by the way. That's shared network, shared compute, shared storage. The whole issue of noisy neighbors just doesn't exist in terms of a distributed and storage environment. Virtualization also can make that a lot worse, because we can have difficulties in actually working out what is going on, because we can only see the outside of the container. We can't actually see what's going on the inside of it.
So the question came in, and I think it's a good clarification question. Can you define sharding for the audience?
Yeah, sorry. You tend to throw these terms around. Sharding is a technique of actually, imagine that you've got data written on a sheet of glass. So you've got a load of bits, ones and zeros, written on a big sheet of glass. And what you do is you smash it with a hammer, and then you take all the bits and you distribute them out to various parts of your kingdom. And then at some point you want to get all that data back. You collect all the shards together and you put them into one object. So sharding is about the breaking up of data. Sharding is what distributed systems do when they're taking very large lumps of data and breaking up to distribute them across various storage nodes in your distributed storage environment. That's the short version.
The short version. Okay, so we've talked a little bit about the strength of the sharing part of it for distributed storage, but what about the installation, configuration, and management of the different storage devices? It seems that intuitively centralized storage might be a little bit easier to install and configure because you're really focusing on one thing. But I see some contradictions to that. John, you want to explain?
Yeah, it's a good point, Jay. So what usually gets simpler is the management of the data. It's easier because again, as you said, I could focus on the data in one location, or rather than in say 10 servers. But as I mentioned earlier, you do need some extra expertise and some extra things to worry about, because you need a reliable network. It has to be enough bandwidth and low enough latency between the servers and the storage. You might need to install special drivers in each server, which are not needed for local storage. And you need someone with some array management skills and maybe network management skills, because again, you may put in a separate network, say a fiber channel network or an InfiniBand network, or a separate Ethernet network, which operates a little bit differently than your standard Ethernet network. So in any case, you have to have that expertise, and you have to think about security and sharing and backup in the array. So it can be both harder and easier. Again, I can back up just one central array instead of 10 servers, but I have to think about sharing an access and make sure that each of those servers only accesses the right data within that array. As you scale up and go large scale with centralized storage, it gets more complex. You have many arrays, and again, you typically, as mentioned in the management part, you have to manage each one separately, and you have to figure out how much capacity each one has and how much is used and how much performance each one can handle. So you have to sometimes shift servers or data around. And since each array is managed separately, automation can be somewhat difficult, but it's probably still easier than if you have local storage in every server.
Excellent. And Alex?
So I'm just going to focus in on two things here. Yeah, sorry, I'm just going to focus in on two things here, Jay, really quickly, because I'm conscious that a lot of this is motherhood and apple pie on the left-hand side. There are two pieces I want to focus on the right-hand side. Those are data amnesia and data migration and lock-in. So data amnesia is something I'm beginning to see a lot of. People forgetting what was put where. It's becoming a really big issue. People spinning up virtualized machines on public cloud services and then forgetting them. You're just quite literally not deleting them or managing them in any sense in terms of their data content and their security, but just quite literally forgetting that they're there. And we're beginning to see an awful lot more of that with this data amnesia. And I don't have any ready solutions for it. It's not something I think that it's controllable, but you actually need to plan for data amnesia. Forgetting stuff is all too easy. The second thing is container lock-in. This is a similar thing to data amnesia in that, okay, you've got containers, but what's inside them? And the data can get locked inside a container and isn't really readily extractable for using for other purposes. So two issues there, lock-in for the container and data amnesia. I think there are going to be bigger issues with distributed storage as we move forward.
I think that makes a great deal of sense. We probably may want to, think about focusing on that as a specific topic in a future session. I think it's kind of important. We're also getting down to brass tacks at this point in time. We're almost done with the presentation in general, but we've also gotten a couple of questions that involve, the costs, right? So, what are the costs? And John, I have to say, I'm not really sure I've seen the word bespoke in one of our webinars before. Someone's bingo card just got really lucky.
That's right. So bespoke, I believe I've taken that from the English or the British English, and it means customized or custom made. Alex, correct me if I'm wrong on that.
No, that's absolutely correct.
All right, thank you. So like a bespoke suit. But centralized storage is usually on custom or bespoke hardware, as opposed to generic hardware. That's usually from a storage vendor or storage and server vendor. It's usually a dedicated platform that does storage only. It sometimes uses a dedicated network, and it's centralized storage. It can be software defined. It can be in the cloud, but that's less common. Usually, it's dedicated hardware and software bundled together, purchased together, installed in your data center, and therefore it's more likely to be purchased through a CapEx model. You buy it as capital expense, and then you depreciate it over time. Although you could use leasing or cloud service providers to turn it into an OpEx. It tends to cost more per terabyte than local storage, but because it's more efficient, you need less of it. So, but then I would say it tends to cost more per terabyte than distributed storage as well. But I'll let Alex comment on that.
Okay. Well, let's let Alex comment on that. Oh, did we lose Alex?
Alex is trying out his new bespoke suit.
I'm sorry. I'm having from. I've got terrible technology at this end of the world. I'm sorry. Basically, what it's about is the economy. It's what it costs. It's what accountants say is the way of doing it. And we are seeing a huge move away from CapEx to OpEx, and that naturally suits distributed storage better because you can do cloudy type solutions and just rent the stuff rather than actually having to buy all your centralized storage. So cost is a big factor. But the one thing I'd point out is we don't know what future costs are going to be, but here's a small guarantee for you. Historically, the dollar per byte cost has fallen pretty consistently. I don't see that stopping anytime soon. I see that actually is continuing on. and things will get cheaper. Somebody's asked the question about the costs in either environment. Ultimately, it costs so much to land a bit, either in a data center or in a distributed storage environment, or perhaps a cloud environment. And the answer to that is, I don't think we really need to know how much it costs per bit from a storage perspective. What we need to work out is what it costs us to run applications across data centers or applications in the cloud. It's a much higher level than this granular piece, but I am guaranteeing it's going to get cheaper as time goes on. The other thing is the application value. I think people need to start valuing applications more than they do the costs of the bits that go up to make it, and that's actually quite a difficult one. But in essence, applications have to be of value, so the bits that make up the cost have to be less than the total value of the application itself. And then new application models are having a pressure because containerless, serverless, all these things are kind of making us question about where we put our data and how we process it.
Okay. I'm going to go ahead and move us a little forward because we are starting to squeeze out of time. But we only have one more category left for our decision criteria. And so last, but certainly not least, in order to cope with the inevitable problems that come up, after all, no solution is absolutely perfect, we need to make sure that we have proper backups. So with everything we've talked about so far, obviously a one-size-fits-all approach won't work. So John, tell us how centralized storage solutions can handle backup and data protection.
Absolutely. Centralized storage is usually very good at simplifying data protection. So first of all, of course, it can have RAID, and local storage can have RAID too, but it's easier and more efficient to do it in centralized storage. And most centralized storage arrays can do snapshots, which are like instant copies of the data that are made on the disk, and usually are very space efficient, meaning the copies don't take up that much space, unless they only take up space as the data changes. And some of these centralized storage arrays can also make clones, where you make a copy of the data that you can then modify or edit or access from a different server. And that data might change over time or might stay the same, but it makes it very easy to use RAID, use snapshots, and use clones, and then you can make a backup of that data somewhere else, on another off the box, just in case you lose the storage box or lose the data center. And this can be done by vaulting or copying some of these snapshots to another box, or to a tape drive or a tape library, or by doing a replication or mirroring. Most of the centralized storage products support some kind of replication where they can mirror all the data to another box in another location to give you some other kind of data protection or disaster recovery capabilities. So centralized arrays, that's one thing that they almost always do well, is simplify your backup and recovery or replication of your data.
Excellent.
And Alex, your turn.
And this time I'm not going to have a technology problem, hopefully. Backup and data protection is an interesting one in a distributed environment because backup can be a lot harder. And in fact, backup needs almost to be done at the application level. Doing it anywhere else doesn't make much sense because backup implies a complete redundant copy, or at least it implies that you have a copy that can be used to recover from some point in time. And CAP theorem and eventually consistent applications might make that a little hard to achieve. I like the diagram on the right. It says backup. You can see that a bit's missing. And I think that's what most people's distributed backups currently look like. It is an issue, but it needs to be done at the application level. The other thing about some of the data that we're putting in the distributed storage arena is not all of it needs to be durable. Some of the data that you're collecting is literally throw away, you can discard it. And if you lose it accidentally, that's actually no bad thing. It's not an issue. Some classes of data are like that. But when you must protect it, avoiding bit rot and device obsolescence, which is the two key things in terms of making sure that we can maintain a long historical trail of data, requires the data to be moved. And that has a cost in its own right, because that implies consuming at least internal bandwidth to move the data about from device to device. There's actually a long-term data retention piece that we're going to be doing shortly called the 100-Year Archives Survey that we've been doing for the last 10 years, and I'd recommend that people sign up for that if they're interested in really long-term data retention as opposed to backup.
Excellent. And we're really getting into the nitties and the gritties at this point in time for the conclusion. So we couldn't obviously get to everything. We've thrown a lot of stuff at you in a short period of time. But what we wanted to convey to you, though, is that these two different approaches represent different philosophies and how it does its one job. A centralized storage solution makes the array, makes each array the center of attention, which can help, I'm trying to do three things at once here, which can help ease some tasks such as backup and security. But there's a trade-off when it comes to scale, and it can require an awful lot of attention and some different ways of thinking about management. On the other hand, distributed storage spreads the performance and capacity across multiple systems, and this provides for the easy scalability and quite often lower costs. The trade-off there is that the security and backup can be more complex. Both ways have their advantages, and hopefully this webinar has been able to help place each into context to help you define your own storage philosophy. Now, this is our 5th Great Storage Debate webcast, and we want to thank you, the viewers, our audience, for making it such a great success. And that means that there are 4 more webinars that go back and ask some of the bigger questions about how to use different storage techniques and when. And this includes everything from block, file, and object I/O all the way to storage protocols and storage management and several points in between. Now, please remember to rate this webcast and provide us with feedback. We always like to know what we did right and what we might have missed. Your input is extremely important to us. And coming up on your screen right now is the link to this presentation. We will be providing a Q&A for all the questions that we couldn't get to as well. So even though we ran out of time, we will still be able to answer them for you. You'll also be able to download that PDF right here on the link that I just put onto your screen. Finally, you may want to consider following us on Twitter to find out more information and announcements of webinars like this one, as well as other events. So from all of us here at SCIA, and on behalf of John and Alex, thank you for attending this webinar, and we look forward to hearing from you soon. And again, please provide your feedback and rating. Appreciate it. Thanks, John. Thanks, Alex.
Thank you, Jerry.